Where are we going?
Cern! When they collide protons, it recreates the conditions when the Big Bang was.
So do you remember a few years back when people were saying that when the Large Hadron Collider was switched on, it was going to make like a black hole?
Yes, Sarah.
What did you think at that time?
I thought I was going to die. We sat in the boardroom and we sat in the boardroom and we all thought we were going to die. We were all counting down the minutes till we died.
Why do you want to go see the Large Hadron Collider?
I want to see it because it would really be a once in a lifetime experience. I never get the chance to do it again, and it'll be something I can tell to my grandchildren.
I'm reading about the Large Hadron Collider, it's very interesting.
Oh, what can you tell us about it?
I'll tell you that in 2008, liquid helium escaped and 100 magnets got destroyed. Oh no. Well, considering they require the magnets to make the protons smash together,
That's true actually.
I can understand why they have 100, and they probably have 100 to the power of the Terra, which I've just learned is to the 12 now.
Ah, cool.
I know.
I'm reading it for them.
It's just fascinating, isn't it?
Yeah. Oh wait. Sorry.
And Steph is actually taking it seriously.
I'm just saying, as an instant, I don't want to know what to do.
The train is double-decker!
Je vais aller lui parler, pas de souci.
So what we're going to do today is we're going to have a presentation now. It's about half an hour here in this room. Then followed by a short movie, about 10 minutes. Then we'll leave. We'll go back. We have a private class. So, no. I think there must be a certain chapel.
This is the hottest place in the solar system. And this is one of the hottest places in the universe. A vacuum, emptier than outer space. The largest number of high-tech magnets ever built. The largest, most complex electronic instrument on the planet. It fills much of the Geneva countryside, but you can't see it, even if you look for it, because to find it, you have to go deep underground. At 100 meters depth, housed in a 27-kilometer long tunnel, the Large Hadron Collider is ready to start.
What's really exciting about this is that some of these new objects or particles are very different to the particles we originally collided together. In fact, they're particles that we no longer see in the world around us. But although these new particles only lived for a short time around the start of the universe, they played a fundamental role in making the universe look the way it does today.
If we want to understand the origin of the universe, one of the ingredients that we need to understand is these particles that last solid and that you cannot find now in mines because they have disintegrated completely from the origin of the universe.
The more we study it, the deeper we look into things, the more we find there is to find out. Because there are some very strange mysteries in the universe.
We know that mass can turn into energy, but we don't know how that happens. We know that back a millionth of a second after the Big Bang, matter didn't exist in the form of protons and neutrons, but in a completely different state. And we know that gravity was extremely important back in those earliest times, but we don't know exactly how it works. But maybe the reality out there is much closer to science fiction than the real world.
But the LHC is lucky enough to penetrate with its very high energy inside these points that contain extra dimensions, then a complete new field opens up of possible new discoveries.
You're looking at 12,000 tons of metal and electronics, which have been put together with a precision of 5 microns. That's 5/1000th of a millimetre. And it's taken many companies, hundreds of universities and research institutes, and thousands of scientists and engineers to put these precision instruments together.
The detectors like CMS and Atlas arguably constitute the most complicated apparatus that science has ever seen.
The LHC and its detectors will produce billions of interesting events every month, but we'll need the computing power of the grid to tell us what we found.
There could be some big discovery about the nature of space-time, or just what's really out there, what's fundamentally there.
We could make a complete series of new particles. We could make wormholes, which are little holes in space-time, in which you can go from one point in space and time to another point in space and time, so that you can travel to another time.
Scientific research is an exciting trip with a fuzzy map and an unknown destination. We are a bit like old-time explorers. We know there's a lot out there to discover, but if we knew exactly how and when we will discover it, it wouldn't be research.
In the most clear and cut and beautiful way that you might hope to look for a Higgs boson. Last year we got 3 events recorded, which looked like they were interesting. So we ran for months and months, 20 million collisions a second, several collisions every time the beams passed through each other, and ended up with just 3 things that look like possibly a Higgs boson, possibly not. So we don't know where we are. So the closest to that by volume is muon systems, trying to measure muons. Why? How many muons are there inside a proton? None at all. So if we see a muon, it tells us something interesting has happened. We've made a collision which has made something new. There's a new particle we made. We haven't just smashed a proton and sent bits flying. We've made something interesting. So it's a tag. It tells us, here's an event where you maybe have created something that wasn't there before. It might be worth recording. We keep all as many of those as we can.
I think I found interesting how big it actually is, because I didn't think that, I knew like obviously the Hadron Collider and stuff were massive like things, but I didn't realise there were so many sites of different things and how many like the big actual collider is, because how long is it? It's about 27 kilometres or something. So I just think it's amazing how many different experiments they're actually doing, and like how much organisation it must take to find all this stuff out.
We are doing crazy experiments with neutrinos, like the fact that we are producing a neutrino beam, and then neutrinos are sent to the Granzasco laboratory in Italy, which is 730 kilometers away. So clearly we don't have a tunnel which is 730 kilometers long. We are crazy, but not that crazy. What happens is that the neutrinos, however, don't need a tunnel because they can cross the rocks. They will cross the Granzasco laboratory, they will cross the sea, they will go out. We're sending millions of neutrinos per second from Cern. We detect 1 neutrino per day in Granzasco.
What was your favourite part so far?
My favourite part so far was visiting Atlas actually, because I've not been there before. And I loved the mural on the side of it that really helped explain what was happening where, and it's reminded me of an awful lot of information that I'd forgotten.
So have you seen the other detectors?
I've been down to CMS and I've actually been and seen it and touched it. It is real, it does exist, I've not just made it up. And that was quite amazing, yeah, that was quite special.
What can you tell us about that since we're not going to see it?
CMS, it's in France first of all, it's further away, and it's in beautiful sunflower fields. It's a great place to work, and it detects in a slightly different way to Atlas, in that it's actually looking for the muons rather than muons just being a slight byproduct. So it's called the compact muon solenoid, and it has some really interesting crystals in there which are very good at reflecting light. And so if they can get the muon to scintillate, which means give off some light, then they're much more effective at detecting muons than Atlas is.
See here is a magnified view central particle detector. So the central particle detector is made of like 13 concentric cylinders of silicon. You can see some prototypes on the silicon here. They're a third of a millimeter thin, and then whenever a charged particle crosses the silicon, it produces a little electrical signal. So we know where the particle crossed. So you know, we see the dots and we join the dots and we reconstruct tracks. Also, the tracks are not straight because there is a strong magnetic field there, 2 Tesla magnetic field, that bends the tracks. It allows us to distinguish positive and negative particles, so one matter and antimatter. And also, the radius of curvature is proportional to the momentum of particles in the transverse plane, so we measure the radius of curvature and we measure the momentum of the particle. The other thing we can see from this picture is that most of the particles are coming from the very center of the detector, but there are 2 of them, these red ones, which are coming from what we call a secondary vertex. It means that there is a particle produced in the center, it travels a few millimeters, and then it decays into 2 other particles, and this is what we observe. Very often we do not observe really the particle was produced directly in the collision, but we observe something that was produced afterwards, the decay process. So in this case, we constructed the produced particle was a Ks, K short, the decay to pi. And 2 muons. So I said that would make Bill happy because those are 2 decay modes of this Higgs boson. So in particular, the 2-photon decay mode is for low mass Higgs boson, and this 4-lepton production is for higher mass Higgs boson. The thing is that there are a lot of standard processes that also can produce this kind of product. For instance, here you think of producing 2 Z bosons, and then 1 Z boson could decay into 2 muons, and the other Z boson could decay into 2 electrons. And for the 2-photon case, there are a lot of processes that produce 2 photons. So the thing is that how do you really find the boson? Well, first of all, you can estimate your background from the theory. But the other thing is that you can reconstruct the mass of the object that produced this. So you can reconstruct the mass of the object that produced the 4 leptons. So you expect your background to have a smooth mass distribution, while if there is a particle with a given mass that produces this object, well, you will find a bump in the mass distribution. So you will find more events than expected from a smooth distribution. On the other hand, well, if you can also have bumps from statistical fluctuations on the background. That's why you win if the signals are small, in order to exclude that little oscillations that you may see are not just due to statistical fluctuations, but due to really something new. Well, you need to collect a lot of data. That's what we are doing now, really. Now.
When we put them into the LHC, the magnets from one of the companies, they don't quite get to full energy. At about 90% of design energy, something moves inside the magnet. There's a little jump of something. The jump means 2 bits of metal rub across each other and cause some friction, and the thing warms up. Now, if you warm up the superconductor, this ivory tin is only superconducting at within 20 degrees of absolute zero, so it will cool down to minus 250. If you warm it up, sorry, it's cool down to minus 270. But if you warm it up past 20 Kelvin, then it starts being an ordinary conductor. Now it's got 12,000 amps passing through an ordinary conductor. It's going to evaporate. It's going to be megawatts of power deposited at that point. So what you have to do is, if you see one bit of the superconductor and stop the superconductor, you immediately have to heat up the whole of it so that it can all become superconductor, all become monoconductor, and then all store power in a magnetic field to store energy. I've talked already about 100 megajoules stored in the orbiting beams of LHC. We have gigajoules stored inside the magnetic field. That energy has to go somewhere. And we flash heat this bit when we've got what's called a quench. But then all the energy from the magnetic field has to get dumped somewhere. It ends up going to heating up this stainless steel. So this stainless steel serves 2 jobs. One is to physically stop the thing moving, and 2 is to try to prevent it from melting when there is a quench. Here is what's called a quadrupole. A quadrupole is very standard. So 2 north poles pointing at each other, 2 south poles. And gives you a kind of square field arrangement. That's obvious, but that it turns out works like a lens. So if you have a system of light, you put a lens into it, you can focus the beam. Similarly, if you've got a beam of electrons, a beam of protons, and you put it into a quadrupole field, you can focus it. So I mentioned already that when we're trying to bring the protons into collision, we like them as focused as small as we can possibly get them. So we have a quadrupole each side of the experiments that focuses the beam down to as tiny a point as it can be to maximise the collision rate.
What did you think of the sextupole?
I couldn't stop laughing. It was very funny, however very socially awkward. Yeah. Not able to laugh at that particular move. I think that was him, bless him, and it wasn't. Yeah,
oh, poor guy.
It was really funny.
And I think you crushed him. I think you crushed him.
Oh, it was funny. It's immature to laugh at sex too. I still find it funny.
In that system, we also have to worry about the beam colliding with the quadrupole, or as well as the detector. So we have lots of bits of tungsten which are arranged to scrape off any bits of the beam that are going in the wrong direction. So that's called collimation. So we have a collimation system which scrapes off any residual bits at the edges of the beam and makes sure we just have a central piece and there's nothing that might bump into the detector or damage it. The collimation system at its most extreme has jaws that are only 2 millimeters apart. So we take this energy, which is 100 megajoules of power, and we send it through a gap that's only 2 millimeters high, and we send it through at 11,000 times a second as it orbits. So that has to not work. And those collimators get hot. The standard problem we have now is that if there's a problem with the collimation system and somebody needs to work on it, we can't do anything until it's cooled down. It just physically heats up. The magnetic field is great for bending the particles and making them orbit, but it doesn't put energy in. It only bends things, it never adds energy. An electric field adds energy. If you've got a 1-volt battery, you take a proton from one end of a 1-volt battery to the other end, you give it 1 electron volt of energy. To get to the energies of LHC, we're talking about 7,000 GeV, or 7 times 10 to the 12 volts. So if we had 10 to the 12 batteries in a line, that would do it, but it would break down. It couldn't possibly work like that. So, but we want to give them an electric field, but we can't do it by having a static electric field. What we have is these cavities. We have an oscillating electromagnetic field. It's a microwave. It's like a microwave oven. An oscillating electromagnetic field in a cavity. But these are very high-tuned cavities. What they do is you arrange to have the size of the cavity matching the wavelength of the wave, and that means it can act as an amplifier, as an oscillating amplifier. It's like when somebody's on a swing. If you push them at the wrong frequency, they don't speed up. If you push them exactly the right frequency, you get up to very high speeds.
Oh yeah, my favourite part of the trip was when we went into the big factory bit where all the extra pieces of the Large Hadron Collider were kept, such as bits of the accelerating chamber, which was cool, and also like that long bit of Large Hadron Collider that isn't used, so it made it look like you were actually down there when you weren't.
What did you learn from that?
I learned about how the protons / charged particles were accelerated. And oh my gosh, I learned about how the magnets worked inside. It's very interesting.
It was weird to learn that they don't get that accelerated in the giant ring, only in the little one.
Yes, because the magnets act like railway lines and that they only guide the particles around the large ring.
This is a current lead. If you think about LHC, it's all very nice having the current going down inside the superconductor, but somehow you've got to get the current into the superconductor. If you just connected those copper wires, the size of my leg, to the superconducting wire, copper is a very good heat conductor. In funnel heating, a superconductor, you could not keep it at minus 270 degrees, so it would just warm up. So you've got to think about how you're going to connect in the power. This is how it's done. This is connected the outside room temperature to a copper wire. It goes down in this rod, which is surrounded here by high temperature superconductor. So this stuff here is all is all cooling. So it always fins so you can cool this down. So this end of the rod sits down at -70 degrees, at which point the high temperature superconductors start working. So now this is high temperature superconductor. It takes the current on down to the bottom end at 2 Kelvin, 1.7 Kelvin. So you don't have a continuous extra copper that runs all the way from the big thick bar down to 2 degrees Kelvin. You have this high temperature superconductors here which are used to carry it through this section. And then there's actually some interesting work going on down the farthest corner of this room at the moment, trying to see what happens if we take these high temperature superconductors and we run them at 1.7 Kelvin. Because it turns out you can put a lot more current into them than you can the standard superconductors. They're really nasty things to make into wires. They're brittle, they're not conductible like a nice wire. But if you could make them into wires, you could make a magnet that's 3 or 4 times stronger than LHC magnets. So there is one at the upper end of this room. It's a test piece. But there is a thought in some people's minds that maybe in 20 years' time we might come back and build a high temperature superconductor version of LHC with 4 times the energy in the same room. And that would be an exciting thing to try.
How much empty space is there in your head? I'm going to say, oh, there's not an option for what I want to say. I don't know, I think it should be 100 really, for my head. I mean, it's actually my head. Or is it yours? Who's the machine talking to?
I think it's the average head.
The average head. I'm going to say, how much? Yeah. Anything made of atoms is over 99% empty. If there were no empty space inside atoms, how heavy would your head be? I don't know this one.
I have no idea.
I'm going to say
the Earth because it's most dramatic. Okay, Mont Blanc, fair enough.
Because it's close to here.
Ah.
Of course I'm right, I knew that all along.
Well, who wouldn't know that?
I said earlier. Build a carbon atom, choose from particles below. It's like 6 of them and 8 of them.
Yeah, if it's carbon 14. Yeah.
Oh yeah.
But it's more
like. Do
likely
you think it would accept?
I think it'd be carbon 12 it wanted.
Do you think it would accept them?
I don't know,
Do you
but
think it
usually
would
the standard
carbon 13? I'm going to try it.
Your standard one in chemistry is carbon 12, but
maybe in your chemistry stuff.
Just remembering that I'm the one who's studying chemistry at the moment, but maybe it is talking about.
No, I know it would accept the normal carbon. I want to see.
You want to see if it'll have a special carbon.
There's like 20 of these, right?
If you wish.
But no. I disagree.
I have to say I'm with you.
I have 6 correct replies. I disagree.
I think there were 7, but anyway.
Yeah.
I hope you see why I say this to last.
How did it start? What is its destiny? For thousands of years, mankind has been wondering about these questions. The LHC will bring us closer to an answer. Everything started at the moment of the Big Bang, 13.7 billion years ago. Time and space begin when a tiny point full of energy starts expanding at an incredible rate. An unimaginable amount of energy transforms into matter and antimatter. But shortly after, all antimatter has disappeared, and only a tiny fraction of matter is left, still enough for all stars and planets in our universe. But it takes almost 400,000 years until hydrogen and helium atoms can form. Now the universe has become transparent. Light
from this era can still be seen today as the cosmic background radiation. Since its awakening, humankind has wondered about its origin, and today we have developed the tools to give answers.
So, what was your favourite part today?
My favourite part today was seeing where the World Wide Web was sort of created.
Yeah, that was pretty cool.
Yeah. I also didn't realise how many other different experiments going on here.
Are you glad you came?
Yes!
Yeah. Very glad.
Very glad. It was really good.
Yeah, I'm really glad I came. I really enjoyed it. I thought it was really fun. I had a really great time.
Did it meet your expectations?
Yes, and actually exceeded them. I thought we'd get everybody fairly enthusiastic about stuff. We had an amazing trip around Cern. I've never done a trip around there that was that good before. The weather was fantastic, and everybody's gone so well, and it's such good fun. I've been blown away. It's been fantastic. One of the best school trip, well, the best school trip I've ever done.
It was a lovely trip. These all brought us together as a group. Everyone's enjoying themselves, and it's a good way to finish our exam.
Bye! This is Lily my towel. For the notes. Maybe you should have got a maxi purple bag.
How art thou?
Then when it would heat up again, it would take about, would it take 3 months or a year?
I can't remember.
3 months for a 300 metre section, because they have like valves which cut it off, and then it's
Saw some really cool things at Cern, and I just had a lot of fun.
Beth's got something to say.
That's what I have to say.
Huh?
He is fit.
Are you glad you came?
Yes!
We got very wet together.
Are you glad you came?
Very glad.
Very glad. It was really
We're on the plane.
We ran experiments with neutrinos.
First time, which is interesting. After that, it's just a repeating cycle.
The best school trip I've ever done.